Yes, hello everybody. Welcome to the performance track. I hope you all enjoyed your meal, and I hope that you're not tired after having your lunch. And because now I want to introduce you to Milian Wolff, who will talk about apps on speed. And well, I know Milian in person. I know Milian from the KDE project, where I've worked with him on KDevelop and on Kate, which is a text editor. And Milian developed his skills further, being a physicist, and he likes to explore and measure things, and so he likes to measure applications. So welcome on stage, Milian.
Thank you. Yes, welcome everyone. It's my pleasure to be here on stage opening up the performance track for this day. It's going to be interesting because we have 3 talks which are all geared towards performance improvements of applications, all targeting a different aspect of what you should be aware of in that regard. This talk is more about tooling. It's about C++ applications and CPU hotspots. And there are a whole bunch of other tools out there which I hope will be presented later to you. With this in mind, let me start. This will be the rough structure of my talk. First, I'll give you a small motivation on why you should care about writing performant code. Then I'll dive into the preparation you have to do before you analyze your applications and try to find the hotspots. What you need to keep in mind when you do benchmarks, these kind of things. Then the main part of the talk, I'll present you a few tools that I personally use a lot in the sense of daily when it comes to a few of them. Everyone should know these tools, that they're out there. Many of them are available free of charge. There's no excuse of writing slow code when you have these great tools out there. And then in the end, I'll wrap it all up with a few small tips and tricks, things I've seen in QtCode when I did reviews while working at KDevelop, for example, for code written by other people. And yes, I hope to at least there give you a few practical code examples on how to write more performant code. So let's start with the motivation. Why should you write code with performance in mind? It's basically quite simple. Qt has this mantra, being able to run everywhere. This is true from the library perspective, but if you as an application developer write really slow code, you cannot be able to run this application on an embedded hardware. If you only have so and so many cycles to spare, or if you have really demanding memory pressures, you need to keep that in mind while designing your whole application. Qt is able to do really fancy animations on embedded hardware, but you as a developer need to make it fly and ensure to use the API properly, for example. Then always there's this psychological thing that faster is perceived better, and thus faster applications compared to other applications in the same field. People will try to, or will probably use the faster application because it makes them more productive. And if you make one thing of your code fly and really fast, it will open up resources which you can then use to implement new features, and then you'll be able to do more in less time, probably even. And then there's this thing which I have the feeling many people so far are still ignoring when it comes to writing code. More and more applications are run on battery-powered devices, and you need to keep that in mind. You need to make sure that your CPU is able to go to sleep every now and then, so saving battery time. Also, when you design applications for the server market, for example, things that run 24/7, the less cycles you need there, the less energy you will drain, and thus you will actually be able to save costs. This is something that Google is doing a lot from what you hear from their presentations, optimizing the code to save energy costs. And at the same time, saving energy, you save some trees. It's also very good. So what do you need to keep in mind when you do performance analysis? There are quite a few things. You can easily shoot yourself in the back when you do uneducated profiling. This is what I did back then when I started learning all this. I tried to be really smart and failed at it. And other more educated people told me what to keep in mind. And the #1 rule everyone told me, and what I always forgot to keep in mind, is that you need to keep the compiler, or you need to let others do the work for you. That means you must enable optimizations and debug symbols. I'll come to the debug symbols later, but if you do not enable optimizations and try to profile your code, you'll find all kinds of funny things. You will find lots of indirections, function calls which are costly. You find that your containers are really slow, things like that. Often this is not true. This is only because you did not let the compiler do its job. So as long as you profile applications without optimizations enabled, you'll end up doing the compiler's job and probably do it worse than a compiler will be able to do it. Thus, always enable optimizations. For if you run GCC, for example, you would pass the -02 flag, Clang similarly. If you use a makefile generator like CMake, you'll pass the -d CMake build type and set it to rel with debinfo, which stands for release mode, but with debug informations. And QMake similarly, you enable release mode, but explicitly pass the -g. Why is the debug flag here? It's important because if you remove the -g and try to profile your code, the tools will not be able to tell you which assembly instruction is related to what file, what function, what line of code. So all you will see is, okay, there is a bunch of instructions which are costly, but I have no clue where in my code that is. So you have to enable debug symbols to be able to figure out where the hotspots are in your code. And then there is the fact that you need to do testing at the same time, or better, first do testing, write the code with the functionality, and then optimize it. That means once you write your code and have it properly covered by unit tests, you'll be able to prevent regressions when optimizing the code. You'll prevent to over-optimize in the sense of removing functionality which some of your user might actually rely on. And once you have a properly unit-tested code framework, you'll be able to extensively refactor it, at the same time being positively sure that you did not break anything. And sometimes this is crucial to do when you want to optimize something. You may need to rewrite some algorithm, you might need to refactor the whole indirections, things like that might induce bugs. But if you have proper unit tests, you can do the optimization in a very rapid way while keeping the quality as is. And then there is this thing about finally doing a benchmark. You first run your application and try to find hotspots. I'll show you the tools later on how to do that. Once you figured out where's my hotspot, go write a unit test, or sorry, write a benchmark. It's different. The benchmark is, you need to write it before you touch the code and try to make it faster. This is important. Be scientific about it. First, benchmark what you have, create a baseline for comparison to later on. Always, when you try to speed things up, do these kind of comparisons. Did I actually make it faster? Don't blindly change code thinking, okay, I really know what I'm doing, it's going to be faster. I added a binary search there, then later on you test it and it's actually slower than before. This is an important trap you fall into sooner or later. So always write benchmarks. It's going to pay off later on. Especially if the function you optimized, someone else might come along and try to optimize it even further. If the benchmark is there, he can be really rapid about doing that and highly productive. You need to minimize the code coverage per benchmark. That means once you find your hotspot, only benchmark this one function. Don't go through tons of indirections. Don't do anything else but the bare minimum which is required to call this one function to actually measure its performance. And then you need to choose an adequate problem size. This means two things. Once, you need to make sure that the problem size you pick is kind of representable for what your users later on will actually use in this function. And then you must make sure that the benchmark runs for at least, let's say, 10 milliseconds. Better let it run over 1 second. Make it artificially long, make it repeat the function over and over again, because otherwise you will end up measuring fluctuations due to random effects like an email coming in, and that affects the performance of your benchmark, things like that. If your benchmark only runs for 5 nanoseconds, you won't be able to tell whether once afterwards it only takes 4 nanoseconds, whether it was random or not. So always pick an adequate problem size. And be aware that QTestLib has this interesting macro called QBenchmark. You pass it a body afterwards, which then gets repeated automatically until a proper problem size or time scale was reached. And then there is the root of all evil. If you Google for that in the when it comes to performance analysis, you'll always find this micro optimizations and premature optimizations. You need to concentrate on the hotspots. Don't try to be fancy and think, okay, this is going to be really slow. I need to spend 2 years of optimizing that code. If it only eventually is responsible for 10% of the runtime of your application. Tooling like the stuff I'll show you later on will actually show you the hotspots. Concentrate on the 90% of the time scale. So that's often 10% of the code responsible for 90%. And premature optimizations means not being fancy when it comes about writing code. You do not have to spend like above normal time scale to write code. Write for functionality first, performance second, but be aware of premature pessimization. I'll give an example later on. If you write a line of code and it's really simple to either make it slow or fast, pick the fast one by default. Don't write very slow code just because you think, okay, I'll benchmark it later on. It's just a waste of time. And then knowledge. Knowledge is really important. When I started profiling applications, I didn't know anything about assembly. I didn't know anything. But the more you do and the more you learn, the better you'll be able to optimize your code. This is really important. You can do lots of useful things even with a bare minimum knowledge level, but the more you know and the more you get to know, the better you will be off. And there are often existing solutions out there. You just need to be aware of them. Use them instead of reinventing the wheel, because most of the time those reinventions will be slower off than the existing solutions which have been optimized for years. This is especially true for what you find in STL algorithm. Qt has its own set of algorithms, don't use them, they're deprecated. But STL algorithms, they're a really good idea. Often they're even faster than what you would write by hand. I once did a really interesting benchmark, just creating a sum out of a list, and I used a simple for loop for that, and I thought like, okay, how much better could it be using STL's accumulate? And it actually was 5 to 10% faster. It's amazing. So always use the STL if you can find something in there which does the job. At the same time, be aware that there exist algorithms out there with a runtime complexity which is better off than something else. A good example here is if you look at QHash and QMAP. One has constant time lookup, the other one logarithmic one. But if you have only very, very small lists, you're often off faster if you use the map instead of the hash, because there's a bit of overhead for the hashing function. Things like that you have to know, and you have to be aware of them. And this is what I mean, that faster code might actually be slower for some problem sets. So with that in mind, we come to tooling. And I'll start with Linux PERF, but with an F, not an V. And it stands for Performance Analysis Tools for Linux. So is cross-platform in the sense of it runs on every platform and architecture that runs Linux, but it's not available on Mac or Windows. But I think more and more embedded devices will run Linux, so this is a very important tool you need to know. It's very fast. It comes with virtually no overhead when running your application. This is done by using a sampling-based wall time profiler. So every, say, 10 milliseconds, it takes a look at your stack and records which function is actually being executed right now, then does some statistics later on it, and presents you the result of which function is probably your hotspot later on. It's very accurate. And it's accurate because it can not only use a very mundane timer, but also hardware and software counters. You can even define your own. You can define trace points. And this will open up a whole new area of performance tools which do not exist yet, but someone has to be creative with the usage of Linux PERF to create these kind of tools. So how do you use it? There's the Linux PERF top function, and that's very suitable for finding system-wide hotspots. It is able to profile us across process boundaries, but because just like the normal top, showing you each process running and how much CPU it's currently using, it does that, but also shows you which function is actually using the CPU time. So in this example, for example, I ran 2 benchmarks at the same time and to get some example data. And here we actually see that, okay, this code is apparently using atomic derefs extensively, probably due to shared pointer usage. And that's actually taking most of the time right now. It's very low level. And you see that there are 2 processes here, quick open bench and bench hashes. These are 2 processes I was running. There are also the libraries showing up. And they are function in there which do take the memory, the runtime performance here. And this is something I'll get to back later. You'll often see that malloc and free and or operator new and delete will show up in your CPU profilings because they are most often the time actual hotspots of your normal GUI application. The less you allocate, the better off you'll be at runtime performance. Once you find a hotspot, for example, with perf top, you can go in more detailed. You use the perf record and report functionalities to first run, for example, your benchmark you just wrote to test the function hotspot you found. And then once you created the report, you actually make it visible. As you will see, it's all command line based. There is no UI whatsoever besides that. It's actually usable. You get results very quickly, but I would love to see a proper UI built on top of it, hopefully built with Qt. If you pass the proper command line switches to perf record, you'll also get the call graph here. Be aware, though, that the data is a bit hard to interpret because the relative numbers here are always relative to parent. So these 65% are 65% of the 98 up here, and you have to do the calculations in your head to actually figure out whether this is slow or not. And another very useful tool is called perfstat. It gathers performance counter statistics on a whole variety of counters at the same time. And this is very, very useful if you wrote a benchmark. You can just run, instead of just running your benchmarks, you prepend it by perfstat and get these numbers out of that. This is most of the time much more reliable than taking a timing, a simple like time your app, to a perfstat your app. You'll see at the bottom also the time that was taken to run the benchmark. But more importantly, you will see how many instructions have been run, how many styled cycles front end were there. That means how much memory, how much time did the CPU need to wait for memory, how many cycles were there, how many branch misses were there, all these kind of low-level details which are interesting in many algorithms you need to keep in mind and try to aim for improve there once you improve the code of your In Qt5, if you write a benchmark using QtTestlib and use the qbenchmark macro, and you call the benchmark with a -perf command line switch, QtTestlib will actually use the perf tool down below in its library to calculate the CPU cycles that were needed instead of the time. You can also define other counters here to use. This is also very useful. But new in Qt5, you cannot do that in Qt4 yet. So to sum up, Linux perf is really good already, but there is so much potential for more. I desperately wait for the time when we have a UI, as I just said, but also what I already mentioned, new tools built on top of perf to, for example, track memory consumption of a tool at runtime without the big overhead of MASSIF, which I will show you later. It should theoretically be possible using this architecture framework. And I hope people in the audience will get creative and try to play around with it. There is also supposed to be support for investigating threading issues in more detail. I didn't get around to test that yet, but this is also something which is not that easy yet in Linux perf. So with that in mind, let's get to the next tool you should all know, which is Intel's VTUNE amplifier XE suite, I think it's called in its full name. It's, you could say, the commercial perf with a good UI. There are lots of features in there which perf does not have at all so far. It's based on a simple or similar architecture. It also does sampling-based time profiling. It's really fast as well. But contrary to Linux perf, it has excellent visualizations in many regards. It has a nice workflow, I think. You need to be aware of, though, that it's proprietary. You need to pay for using it. There is a free license available for everyone, though, if you do non-commercial work on Linux machines. So at least if you want to try it out, run it on your pet project on a Linux machine, and this gives you good input on whether you want to buy it or not. The thing about it, though, is that it does require Intel CPUs for most of its features. So for the embedded market, it might be not the best choice. Yet with Qt development, my experience is that developers work on their applications on their desktop. And if they make it fast there, for example, using Intel VTUNE, and then deploy it onto the embedded platform and test it there, they'll see it's going to be faster there as well. So I think Intel VTUNE has a role here as well. One thing it does much better, I think, than perf or any other tool is that it gives you an overview about the profile data it just analyzed. So the first thing after you run a benchmark is that it actually shows you, for example, the top 5 objects where CPU cycles were burned, or in this case, where threading issues are, or where threads waited instead of actually doing useful work. You'll see a thread concurrency histogram, which then shows you how many threads were running at the same time and doing something. If you want to be multi-threaded, on this machine, for example, you want to be here. As you can see, this is really poor, as it says down here. In average, only 1 thread is actually doing work, and sometimes 2, maybe even 3 threads are running, but there is definitely a problem here. I'll show you in 2 slides how VTUNE helps you in finding these issues. It is able to detect CPU hotspots, and you can see the call graph in a nice manner. You see where in your code, in which function, how many seconds were spent. You can not only traverse this tree bottom up, which is oftentimes the best one to tackle a performance issue, but if you need to, you can also go top down up here, which is sometimes very important as well. In this artificial benchmark, for example, I looked at QList. I want to take this slide as the first Qt tips and tricks. In your own code, do not use QList by default. Never do. Always use QVector. Especially use QVector with custom structs, for example. And declare them as movable. This is done with the QDeclare meta type and then QMovable type. If you download the slides later on and click on the link here, you'll find a long article by my colleague Mark Mutz explaining why QList is not the proper choice by default for any container. Qt itself does it, sadly, and we hope in Qt 6 maybe to improve this eventually. But do not follow that trap in your own application code. So I said VTUNE is able to investigate threading issues. This is the so-called locks and waits analysis, which shows you which function actually triggered a wait of the CPU. So whenever you have a thread and, for example, try to acquire mutex lock, you might content and then not go ahead with working with doing something useful. Instead, you will wait. And in this example, you see lots and lots and lots of these locks and wait for update and wait for whatever. And these things are always issues when you write multi-threaded code. Keep in mind, though, in this view, you might see at the top, especially in Qt, that the event loop shows up. This is actually not bad. This is actually good because your program was idle and waited for user input, for example. So waiting is not always bad, but most of the time if you see lots of mutex locks, for example here the Q mutex lock inline or this simple pthread mutex try lock, this is a bad idea. I really suggest you, if you write multi-threaded code, do not ever try to use QMutex. There are other ways in designing multi-threaded code where you do not need any locks at all. Use a proper library such as KDE's Threadweaver or Intel's threading building blocks or Apple's libdispatch, which is cross-platform as well. And that allows you to write asynchronous task-based multi-threaded code, which performs much better than if you write these kind of mutex, lock, unlock, have tons of race conditions. It's so complicated. Don't go down that route. It's horrible. I will show you later on even an example on how to do this quite nicely in Qt with signals and slots. Besides what I showed you just now here, VTUNE is also able to show you this, the per thread CPU usage and the context switches it did and the waits it encountered while profiling your application. You see here at the top the per thread CPU usage. That's the brown things you see there. You see yellow transitions in between. These are context switches due to mutex locks and unlocks and atomic reads, writes, and waiting. And this is always a very bad thing to see when profiling an application. And it's really hard to rip it out because essentially you have to rewrite the whole code and make use of asynchronous API. So do it from the start correctly. You will see in these graphs the background is either dark green, so the thread was running, or in this gap here you see really nicely that the thread was waiting and couldn't do anything at all. So this is a kind of visualization I was hinting at. This is really excellent if you want to figure out where are my threading issues in my code. And Intel's VTUNE is excellent in that regard, I think. And I hope eventually we'll get similar UI for Linux PERF, for example. So yeah, again, prefer the async API. Also something which you'll find often in other talks by smart people in the C++ community is that they suggest using value semantics. This is something I personally also only am starting with grasping in its totality, but what I see there is it makes it possible to write highly efficient C++ code in a threaded environment because you suddenly do not share any data between multiple CPU cores. And this makes it possible for those cores to run independently and much faster without any synchronization in between. This is highly, preferable over anything else, like shared data all over. Probably then you need mutexes again and so on and so forth. Yes, with that in mind, we come to another tool. It's VALGRIND, the so-called developers Swiss Army knife. It's available on Linux, it's available on Mac, it runs on x86, on ARM platforms. There is, as far as I know, an experimental tool for Microsoft Windows as well. I do not know how it works or not, but yeah, there is someone working on that. And there are two tools in there which are really recommendable when it comes to profiling. That is QtDD13 and MASSIF. VALGRIND is a deterministic instruction profiler, and MASSIF is a heap profiler. The former does CPU hotspot finding. The latter is the only tool I know of which gives you a really nice overview of where in your code do you allocate memory, how much do you allocate in total, and then gives you the possibility to improve on that. Sadly, VALGRIND comes with a huge cost. It essentially emulates your CPU and runs your application on that emulator. And that makes it really slow. Often you have an overhead of 20 to 100-fold. It comes with a large overhead, especially in memory space, so most of the time you won't be able to benchmark your app directly on an embedded platform, for example, because there's simply not enough memory to run VALGRIND. And to make things worse, it becomes more and more complicated to run VALGRIND on any kind of modern application, because most of them nowadays use a JIT compiler internally somewhere. Qt, for example, has nowadays one in QtScript, QtWebKit, QML, and QRegular expressions, and I might have missed some others. So whenever you use anything that might be JITted, you need to pass the SMC check flag to VALGRIND, otherwise it will randomly crash and you'll not see what's going on. Be aware of that. But once you did get data out of VALGRIND, it is really nice, and it gives you a whole depth of information about your application. And it's deterministic. This is something the other tools, because they're sampling based, cannot give you. They're only statistically deterministic, but have like deviations due to random nature. Because VALGRIND actually emulates the code, it can count instruction by instruction and actually knows what's going on there. And KCACHEGRIND is the tool of choice to visualize call-grind data. Is very nice tools from the KDE community, and I highly recommend using that. And I hope in the future to spend some time on getting PERF data visualized in KCACHEGRIND. That would be at least a good step forward in that regard. Down here, if you look at the slides later on, you'll find some hints on how to improve the output if you look at Qt code, but yeah, I will not go into that right now. Yes, when you look at MASSIF output, you need a visualizer for that as well. This is MASSIF visualizer, actually written by me while working at KDAP. And it shows you here in the graph view at the top the total memory consumption. That is the total heap consumption. You can also look at stack, but most of the time you don't need that. Sorry. And down here, the stack graphs are the so-called memory hotspots. These are the functions which allocate the most memory at one point or the other. At the right side, you'll see each snapshot and the call graph it has. There's also an option similar to KCACHEGRIND. Let me go back here to view these kind of call graphs in a MASSIF visualizer in another tab. I'm not showing it here right now. And this gives you the possibility to actually figure out, okay, where are my memory leaks? Where am I using much more memory than I would have expected? How can I improve that? This is otherwise really hard to find. MASSIF makes this really simple. And it's not only about memory consumption, it's also about speed. The less memory you consume, the faster you'll be. Especially lots of tiny mallocs will often be quite slow if you can somehow restructure your code, reuse data you allocated. Things like these really speed up your code. I'll show examples later on. Yes, with that in mind, I come to more or less, I think, the last tool I have, which is mostly just shell scripts making use of PMAP. PMAP is a small utility available on Linux machines. It makes it able, or it gives you an overview about the memory that your process is using right now, but on a very high level. It's not going like, it cannot show you in which function the memory was allocated, but only gives you the total overview of heap consumption and resident set share size and things like that. It's working really nicely on embedded Linux. This is actually why I wrote it while working at KDAP to investigate memory issues we encountered on a embedded Linux system. It could easily be ported to OS X or Windows. You just need to exchange PMAP with whatever you have available there. Quick Google, I found that there's something called VMAP, apparently, and that should probably be easy to replace in the scripts you can download at GitHub on my profile. And yeah, there are two scripts. First, the one targeted at single processes, again, mostly for benchmarks. This is interesting. You can run your application really long. There is essentially no overhead because only every, I think, 1 second or so, it takes a data point of how much memory is used right now and writes it into a file. It's very cheap. And then you can visualize it with GNU plot. Yay. It's not interactive, but at least it gives you an overview of how your memory is evolving. And you can, from that alone, find whether you improved your code or not, whether there are any issues, unexpected memory peaks, things like that are you need to be aware of. And more often we encounter more complex software systems with multi-process architecture. We see dbus talking between these processes. And we need to be able to figure out and correlate the memory consumption, for example, of these processes. And with PMAP, it's straightforward to investigate all these processes at the same time. Actually, if you do not pass any filter, it will just go over all processes it finds on the system and records the memory consumption for all of them. At the top, I didn't show it here, it will also show you the total used memory and the total available memory, so you can correlate maybe your total used memory hits a barrier there, and you end up with kernel issues because it tries to free up memory in some places, removing cache effects there, in fact affecting then the performance of your application and so forth. So this was already very useful to us in production use. So yes, with that in mind, I come to my last, well, relatively short section about tips and tricks in Qt. I already mentioned, do not use QList, use QVector with movable types, or even StudVector. It's also very good, even better in most cases. Then, if you write associative containers, prefer QHash over QMAP. Or at least if you can make sure there are more than never more than 10 elements in the list, then probably QMAP is better. But who needs a list of 10 elements and does this in high frequency, anyways? But yeah, keep that in mind. QHash is often better than QMAP. Besides, you need sorting. But yeah, keep that in mind. So yes, let's come. Oh, that's always showing up already. Sorry. QString allocations in this code. It's a very small snippet I came up with, and it looks harmless, I think. And it's a perfect example for the case of premature pessimization, in my opinion. You write this code, it's really simple. It just checks whether some long string contains at position 42 the string my needle. What's wrong with that code? Who sees it? Yes, Bernard? Yeah. This is the first place, .mid. What's wrong with .mid? .mid actually creates a copy of the string range from pos and the next needle size elements. You can use .midref. It gives you a string view with, so to say, a stripped down API of QString without any allocations at all. So yeah, there is one more allocation. And that's only something you can fix easily in Qt 5. In Qt 4, you need to restructure the code a bit more. But in Qt 5, you even have the possibility to get rid of the allocation here. Because at runtime, this string literal needs to be converted to a QString. That's by default a UTF-8 string, the characters in here, but QString internally is UTF-16, so there's conversion happening as well. And it's really simple to make this run much, much faster. Let's get run. You just call .midRef. There's no allocation anymore here. You get a string view, which is really cheap. You can do the comparison to your input string. That's fine. But still, we have the string literal down here. In Qt 5, with the proper compiler, you can get rid of the allocation down here by replacing or wrapping the string literal in a QString literal. And then the compiler at compile time will do some magic based on the magic in the QLibs to construct a QString in read-only data and have it usable at runtime very efficiently. What's the difference? Who would guess something? Is it fast? Is it really noticeable? No. So I was thinking, let's say maybe it's 2 times faster, right? I mean, still most of the time I'll compare strings, right? This is going to be slow. But no, the allocations are actually the worst part of that code before. Now I saved nearly 1 order of magnitude of runtime just by getting rid of allocations. Then the code is cached and it's much, much faster. So these kind of things you need to keep in mind when writing code. Don't use .mid most of the time. Use midref, especially when you only need to temporary and can make sure that the lifetime will be guaranteed. Especially when parsing data, most of the time you will be able to do that. And proper API, for example, Qt's XML patterns library actually makes use of QString ref as well to speed things up and prevent runtime allocations. So while we are talking about QString, there's something else I found often is the need for, so to say, tokenizing an input string. For example, you read something from an input file and then you tokenize it and create a Q vector of QString. It sounds simple, right? We have some logic to find tokens and then essentially just do again a .mid and start and end of our token and append it to the Q vector. Here we cannot easily use .midref because we need to store the Q strings in a vector and it might get used sometime later when the input string is gone, so you cannot store QString ref here. You need to be make sure it's efficient. But most of the time you parse some kind of input data where you can actually predict the contents. There will be repeated keywords. Here, for example, assuming the common input will be foo and bars and whatever else you can come up with. So how can we improve this? Instead of calling the append to my vector directly with the .mid of my input string, I'll wrap this .mid with a function call I'll show you later, and you pass the midref to this function. So, oh yeah, and this is something I forgot, sorry. Here, while running the tokenize function, you'll have actually a 100% memory overhead. That means you have the memory stored in input, and while parsing it, you'll create a copy of the input for every token. And eventually you will have most of the input copied, and so you'll need 2 times the memory of your input string. If you instead introduce this token text function, which takes a QString ref, and create, at compile time, a list of keywords which you expect. And then instead of doing some manual iteration, use std_find algorithm to find the string ref in this list of keywords. And if you find something, you return the string here from the list of keywords. Remember, this is all compile time. And then you'll not need any allocation to convert the string ref to a QString. And if you do not find the keyword in your list of predefined keywords, you have to go the slow path and return a token to string. So there is an allocation here. Could be optimized later, but this was simple. How's the speed difference? After all, we need to go over our keywords and find it. In the artificial benchmark I came up with, it was numbers like, it was faster, that's my point, it's not slower this way. And actually, the biggest advantage is that you do not have any memory overhead when you have input files with predefined keywords, because you do not need any allocations to create these token strings, because you just reuse the list of predefined keywords in your list here. So in my benchmark, it was a difference of, I think, 22 megabytes or something like that. Oh yeah, and if you want to look for this, it's called interning in other languages, and yeah, you need to be aware of it. For example, QString is implicitly shared. That's why this all works. I hope you are aware of that. But QString does not intern things automatically. So if you create a QString of string A, and then later on again create a QString of string literal A, these two will not share memory if they're in different translation units. You have to make sure to actually assign them or copy them or use a pattern like this to share memory here. So yeah, with that I come to the last example, thread-safe message passing. I was going on and on about do not use mutex logs, and even if you do not want to use some kind of library, for example, Threadweaver in KDE, you can very simple come up with a minimal API for your own use using only QObject and signal slots, because signal slots are thread safe. You just create some kind of worker object. It's a bit of code here, but essentially you could rewrite that, get a functor in, and have it work for all kinds of function you want to process in the background. So somewhere you create a Q thread, and then you create a worker for that thread. See how this worker does not have any parent. So you do not set the parent to thread, but instead you move the object to the thread. And to have it cleaned up properly, you connect to the finished signal, assuming the thread is running. But yeah, this is just to get it on one slide. And then you have your public API, for example, work. And work gets some data. It's value semantics, more or less. You get your input data, and then need to make sure that this function is thread safe. Because remember, the worker function itself lives in a different thread. If you have your GUI thread and want to call worker work, you need to make sure that this work function is actually called in the background thread. And to do that, you go the indirection through the QMeta object invoke method. This then dispatches a signal which is going to be calling the internal work function down here, but in the context of the thread we created here. So this makes the function down here thread safe, because, well, it's not being called from anything else, but more importantly, this one is thread safe. And you can pass any kind of input data here. You just wrap it up in QArg, dispatch it, and then here in your internal work function, you can do anything. You do not need any mutex, you do not need any atomics. You just work on the data very efficiently. And then once you're done, you emit a signal down here. You then need to be connected to that signal in your main thread to be notified, okay, the worker has finished processing the data. But this again will go through the event loop, and it's highly efficient, and it's much better already maintenance-wise than using QMutex. And I would always recommend using a pattern like that if you are afraid of using a library for these kind of task-based asynchronous APIs. But as you can see, Qt offers you all you need to write relatively good threading code by hand. So with that in mind, I come to the end. Are there any questions?
Thank you, Milian. I hope that, thank you for a nice talk, and I think that everybody has now I hope that everybody has now some new ideas what tools to try out next. Are there any questions? Okay.
For the last example, why not use Qt concurrent run with QFuture?
Qt concurrent I deliberately left out because I think it's not good to use it yet. It has multiple problems. The biggest one is that you cannot define which thread pool it's going to run on, as far as I know. So you'll end up with always using the same thread pool, even for or runnables which are distinct from each other, like I/O jobs blocking CPU jobs and vice versa. And there are other libraries out there which I would recommend in favor of that every time.
Thanks. Anybody else?
In the last example, could you have also, instead of invoking your work in your internal work method, making it a public slot, and from the code which calls your invoking method, just emit a signal and connect this signal to this slot? It would be the same thing.
Yes, exactly. It would be the same thing, but personally, I find that a bit well. This is like a proper C++ API, right? I just call a function on my worker object. I do not call something on the object I'm using it on to dispatch the signal. This is always safe. You cannot shoot yourself in the foot by accidentally calling the not thread safe function, which you would maybe be able to do in the other way. So this is just my pattern. If you prefer the other one, it's perfectly fine as well, yes.
You told that it's a good idea to write on QBench to find out where the bench problems are before doing the changes. And if you have a performance problem that is a call to a function that is outside of the unit, how do you handle this?
Two things. First of all, the benchmark comes after you found the hotspot. First, you run your tooling on your application and find the hotspot, and then you create a benchmark specific for the hotspot you found. And you need to make sure that your code is properly modular and isolated such that you can create a minimal benchmark running on that. It is kind of in the sense of, let me go to the beginning, where I said that you need to make sure that you test your code. Because as soon as you have your code properly tested, it should be trivial to create a benchmark because you already have a test unit test for it, right? So just calling a function more often in a QBenchmark should be trivial.
But if the performance problem could be that calling the function at all, so if you could just leave it out and find another way to get your data.
Yeah, that would be optimal. That would be the best thing you can do performance-wise. Removing the function, it's going to be much faster.
But how do you test this in forward to ensure that you have increased performance?
Well, you need to pick the proper level of benchmarking there. It's specific to your use case. Most of the time, you will not be able to just remove it altogether, but always you will have some function at the top, some logic you need in your application, and that is slow. So you call that one and try to optimize that. And if internally it calls some function which is slow, you can optimize that and see the effect on your own code.
Yeah,
so
okay.
It depends on the application or on the use case and problems case.
Thank you.
Yeah.
More questions? No, no questions?
Quick one is there something like a performance monitoring tool that you can use from a different machine? So that you could, running something headless, for example, on a server that you want to constantly monitor performance.
Yes, definitely. VALGRIND, for example, just calling callGrind perf stat does not use any UI. Actually, the whole perf tool suite you can use on a server and just create the data there, then send it over to a client and evaluate it there and report the data. That's
you would have to have a shell on the machine that runs the server.
Yes.
Okay.
Well, yeah, but most of I mean, I know that people integrated it in Jenkins, for example, the build bot to just run perf stat on my benchmark, things like that is possible. Even VTUNE has standalone command line tools which you can run on a server, for example, to get the data, but to actually analyze it later on, you need the UI then.
Of the asynchronous libraries that you mentioned, is there any that you specifically recommend?
Personally, so far, I mostly work with KDE's Threadweaver, but I heard lots of good praise about both libdispatch and Intel's threading building block. And contrary to VTUNE, threading building block is actually cross-platform, and you can run it on ARM, on AMD, whatever. It's, I think, free of charge. You can use it. So personally, I would try that one next. libdispatch is new to me, but it's supposed to be very good as well.
And speak something against using Qt concurrent, or it's out of scope of your...
I said that before. I do not like the fact that you cannot easily distinguish between, for example, I/O jobs and CPU jobs. And but I think they want to improve that in the future, in the near future even. So maybe it's going to be better soon.
Thank you.
Hier vorne.
Could there be any reason to use QList rather than QVector?
Definitely, yes. Yeah. But these are really, really rare circumstances, in my opinion. So far, I think I never found a case where the QList would be faster. But the thing where it is supposed to be faster is if you do not append from the end, but need to insert something in the middle or at the beginning. For example, a Q. That would be a bad choice for QVector. But there's QQ, which is internally implemented using a QList. So there, for example, I would also use the Q because that's the proper API. But even if you do the benchmarks and try to figure out when is the QVector becoming slower, because, I mean, it has to move the whole chunk and reallocate and everything, you need to have really large lists to make it worse than the QList way. The article I linked to by Mark Mutz is actually going into that and showing benchmarks and shows at which point the break-even is. So at which point or which list size or input data size QList becomes better than QVector. But this is again something you need to benchmark and see whether it affects you or not.
You said at the beginning that the Qt algorithms are deprecated or something like that.
Yes, my working colleague Giuseppe D'Angelos, he's not here, I think, at this conference, but he told me when reviewing the slides that I should mention that maybe it's not yet deprecated, but it's going to be deprecated. I think he's working on that, and everyone, in my opinion, should not be afraid of using STL. Smart people work on that, and I think many more people work on STL algorithms than Qt algorithms. So yes, I would say prefer STL's algorithm header.
Okay, thanks.
Here in front is one more.
How good is the integration between the STL algorithms and the Qt containers?
It just works.
Okay.
Because Qt, since Qt 4, I don't know whether even in Qt 3 had STL, an optional STL layer, so to say. That's the iterators, the .begin, .end thing. And in Qt 5, as far as I know, you actually need to compile with STL compatibility. So it's guaranteed to work.
Okay.
There's one.
Hello.
Hi.
Sorry. What about STL containers? Would you prefer them instead of Qt containers? Thank you.
Personally, when I write code, I use the Qt containers, but mostly because I like their API a bit more. It's just a matter of taste.
They have better syntax, I think. Better syntax.
It's if you like the Qt style of programming, you'll get to love the Qt containers, of course. And when you benchmark it, it's actually fun. some parts, some usage patterns are actually faster in at least one benchmark I know of in an application I work on, where QHash was faster than a STL unsorted map, but maybe because unsorted map is relatively new. And still, I think there's nothing against using stud containers. They're very good, in some cases even better, especially with move semantics. Instead of this strange QDeclare meta type thing, which is very Qt specific, you can use the proper C++11 API to make things movable. And then the stud containers will be more efficient, because so far the Qt containers do not make use of move semantics as far as I know internally. And one reason why you should always use Qt containers is as soon as you interact with a Qt API, you do not want to convert from one container to another. That's the same thing with QList and QVector. If at one point you need to pass a QList of something to a Qt library API, use QList from the beginning. Do not convert it to a QList whenever you call the function. And that's the same here. If you have internal data which you're never going to hand over to Qt API, it's fine to use stud containers.
Thank you.
Okay, maybe one short question.
Okay.
Okay, so then I think that's it. Thanks again, Milian.
Yeah,
Let's give him a hand.